Chapter 5, Section 8, Inverse Trigonometric Functions, Differentiation. So in Section 8, we're going to look at differentiation, and then we're going to kind of reverse things in Section 9 and look at integration involving inverse trig functions. Now, remember, with inverse functions, only one-to-one functions have inverse functions. And as you probably know, if you can picture the sine wave or the cosine wave, the trig functions, the 6 trig functions, are not one-to-one. And therefore, they wouldn't have inverse functions unless, of course, we make some adjustments. We limit the domain so that we get a one-to-one function, and then we can go ahead and determine the inverse function. So I'm going to go ahead and define the 6 inverse trig functions. This should be mostly review because of your days in Algebra 2 and pre-calculus. So y equals the arc sine. Sometimes instead of writing arc sine, this book that we use is a little bit more old school. Sometimes what you'll see is you'll see it written like this, where this is the inverse sine of x. Arc sine and inverse sine of x, they mean the same thing. I like this a little bit better because I'm an old man and I like old school stuff. This sometimes I think students can get confused. They think that the exponent is -1 when it's written this way. But it doesn't mean that. It means the inverse trig function, the inverse sine, and so we can write it either way. Now, y equals the arc sine of x if and only if the sine of y is equal to x. Remember, if you interchange the variables. So recall with the sine that the domain for sine is all real numbers, so we limit that to just between -pi/2 and pi/2 inclusive. And of course, the range for sine is -1 to 1 inclusive. So of course, the domains and the ranges get switched on the inverse function. The domain is from -1 to 1, and the range is from -pi/2 to pi/2. I would take the time, if I didn't already have this, and I would definitely memorize the domains and ranges for the first 3 inverse trig functions. Y equals the arc cosine of x if and only if the cosine of y is equal to x. You can see the domain, same as the domain for arc sine, between -1 and 1 inclusive. But in this case, we're looking at first and second quadrant angles because cosine is negative in the second quadrant. So we want between 0 and pi inclusive. Arc sine, of course, the arc sine, arc tangent. Of course, the tangent function, you have some restrictions because of the fact that you're going to have a variable in the denominator for tangent. So what we're going to do is we're going to look at, for tangent, only those values between -pi/2 and pi/2, not inclusive, and then that way we can have a one-to-one function, the y equals the arctan of x if and only if the tangent of y is equal to x. The domain, all real numbers, just as the range for tangent is all real numbers, and in this case the range is between -pi/2 and pi/2, not including the endpoints. It's undefined at the endpoints. These 3 we don't see quite as often. I'm going to go ahead and have them written out for you to look at, and you can refer back to them. But I don't think I've ever come across a problem on an AP, a practice AP test, or an old AP test that had to do with knowing the domain and the range, or the range for these 3 here. Okay. Now, but they're listed here for you, and you can look through that as well. Now, to evaluate these, some students want to immediately grab a calculator. I prefer to do this slightly different here. I have the arc cosine of -1/2. Now, -1/2, that's one of those values you've seen for cosine. Anything plus or minus 1/2, plus or minus square root 2/2, plus or minus square root 3/2, 0, plus or minus 1. Those are all values that you've seen. Now, what this is saying is the cosine, that this is equal to, this is an angle, by the way. You take the cosine of an angle, you get a number. You take the arc cosine of a number, you get an angle. This is saying that the cosine of some angle, and this angle would be between 0 and pi inclusive, is equal to -1/2. Now recall, in the first and second quadrants, cosine's negative in the second quadrant, so this is clearly a second quadrant angle. And the cosine of what second quadrant angle is -1/2? Well, that tells me that that angle is going to have to be 2 pi over 3, because I know that the cosine of 2 pi over 3 is -1/2. Therefore, the arc cosine of -1/2 is 2 pi over 3. Now, if you punch that in on your calculator, you're just going to get a decimal approximation, but it's nice to be able to come up with the exact values, and it also gives you more meaning because you know what quadrants you're looking at a little bit more readily. Arctangent of 1 is equal to what? Well, again, it's equal to some angle. Here, this time I'll just go ahead and write equals alpha, such that the tangent of alpha is equal to 1. Now, because tangent of this angle is positive, and we know that we're looking at a range between negative pi over 2 and pi over 2, this is in the fourth quadrant and the first quadrant. Fourth quadrant, not like 11 pi over 6, kind of an angle. Fourth quadrant like negative pi over 6, because it's got to be between negative pi over 2 and pi over 2. Well, in the fourth quadrant, tangent's negative. In the first quadrant, tangent's positive. I know that this is going to be a first quadrant angle. Now, which angle is it that has a tangent that's equal to 1? Well, that's when the sine and the cosine are the same. That's at 45 degrees or at pi over 4. So alpha would be pi over 4, which means I could say that the arctan of 1 is equal to pi over 4. I prefer radians here. I mean, if you use degrees, I would understand that, but try to get into the habit of using radians in this section. The arcsine of 0 is also an angle that indicates that the sine of this angle is equal to 0. Well, that happens at 0. So that tells me alpha is going to be 0, which tells me that the arcsine of 0 is equal to 0. Okay, let me move this up just a little bit. Now, the next couple are a little bit tougher. For tangent, most people remember 1 and negative 1, but they sometimes have trouble with square root of 3 or square root of 3 over 3. But this is one of those multiples of 30 or multiples of 45, multiples of pi over 6 or multiples of pi over 4, kind of an angle value. And this is equal to some angle. It's going to be in the first quadrant because it's positive, such that the tangent of this first quadrant angle is the square root of 3 over 3. Now, I know that the square root of 3 over 3 might not come to you right away. It is the same as 1 over the square root of 3, and that's the same as 1/2 over the square root of 3 over 2. Now, most people don't think of it this way, but if you do think of it this way, and since tangent is the sine of the angle over the cosine of the angle, I'm trying to figure out what angle has a sine that's 1/2 and it has a cosine that's square root of 3 over 2. Well, that's 30 degrees or pi over 6, so that tells me that the arctan of the square root of 3 over 3 is pi over 6. I can imagine on that one I'm going to have a lot of decimals because students will have a tendency not to be patient enough to go through all these steps. But it doesn't hurt, and it's nice to get an exact value when possible. Now, in this case, I cannot get an exact value, and then all of a sudden you say, well, that's not helping me because this is an arcsecant, and I don't have an arcsecant button on my fancy calculator. Don't worry about it. This is an angle. Now for arcsecant, it's in either the first quadrant or it's in the second quadrant, because just like cosine, positive in the first, negative in the second, and this is a positive number. So I already know it's a first quadrant angle, and it's a first quadrant angle in such a way that the secant of this angle is equal to 1.9. Well, that tells me that the cosine of this angle is 1 over 1.9. because cosine is the reciprocal of secant. And now I can use the inverse cosine button to figure out what this is. And I think I've already done it on my calculator there. Let's see if you can tell what that is. There you go. The inverse cosine of 1 over 1.9 is 1.0165. I'm going to round it to 3 decimal places, 1.017. 1.017. Arcsecant of 1.9 is 1. What did I just say? 0.17 approximately there. All right. So you may have to depend on a calculator because you may get a value where it doesn't come out to be a multiple of 30 or a multiple of 45. All right, properties of inverse functions. Now these are properties, again, these are properties you probably already know. I'm just going to go ahead and make mention of them. And that is if x is between negative 1 and 1 inclusive, and y is between negative pi over 2 and pi over 2 inclusive, that the sine of the arcsine of x is x. They're inverses. They cancel one another out. And the arcsine of the sine of y is y. Now that doesn't mean that every time you do one of these things that you get the same exact value. You will most likely here, but not so much here. And I'm going to show you an example in just a bit here. But as long as you have these restrictions, then this is always going to be true for either one of these cases. And in here, if negative pi over 2 is less than y is less than pi over 2, the tangent of the arctangent of x is equal to x, and the arctan of the tangent of y is equal to y. And then down here, if the absolute value of x is greater than or equal to 1, and y is between 0 and pi over 2, or y is between pi over 2 and pi, including 0, including pi, then the secant of the arcsecant of x is x, and the arcsecant of the secant of y is y. Now you may wonder, well, they did the sine, they did the tangent, they did the secant. How come they didn't do the cosine or the cotangent or the cosecant? Well, you're going to see that in just a little bit, because when we look at the derivatives of these functions, there's some similarities, some very strong similarities. But let's go ahead and do a little bit more pre-calculus here first. Let's evaluate here that I am taking the arcsine of the sine of pi. Now, based on this, it should be pi. But look right here, is pi in that restriction? No, it is not. The sine of pi, you may remember, is 0. So this is the arcsine of 0. Well, the arcsine of 0 is 0. It's not pi. Okay? Because you have to have an angle between negative pi over 2 and pi over 2. So this is equal to 0. The arcsine of 0 is 0. We just did that a little bit ago. Back here. Oop, back here. That it was equal to 0. All right, now let's try this one. The sine of the arcsine of 0. Now in this case, I think we're going to be okay, and you're going to see this ability to use the inverses a little bit more readily, because in this case you see how I have a 0 here, and that is certainly between the negative 1 and 1. So the arcsine of 0, take the sine of that, it should be 0. Let's figure it out though. Let's make sure. What is the arcsine of 0? Well, just 2 seconds ago we said it was 0, and the sine of 0 is 0, just like we would have expected. All right, let me find another page and notes here. Ooh, here's an interesting problem. In this problem, it's actually asking you to solve an equation. Now, I'm going to try to find an exact value here, so I may end up leaving my answer in kind of an odd manner, but let's see what's going on here. Now, this says that the arcsine of 5x plus 1 is equal to pi over 6. Now, what do we know here? Well, we know that the arcsine of a number is got to be an angle, and that's what I have here. But this number here, this has to be between negative 1 and 1, right? That doesn't mean x has to be between negative 1 and 1. It just means the expression has to be. So I am going to take the sine of both sides. And I end up with here, using the inverses, 5x plus 1 is equal to, I guess this one's going to come out better than I was thinking. For some reason, I was thinking it was going to have kind of an unusual term in it, but it looks like it's going to work out just nice. So if I now solve for x in a traditional way like we did back in our 8th grade class or 7th grade class, subtract 1, divide by 5, I get negative 1/10. Now, if I plug negative 1/10 in here, 5 times negative 1/10 is negative 1/2. Plus 1 is certainly in that negative 1 to 1 range. This is a good answer. Okay. Now, this one's a little bit tricky. At least students that I have worked with in the past seem to find this one a little bit tricky. I don't think it's all that bad myself, but then, what do I know? So what I'm going to do here is I am going to solve and find the cosine of y, but my answer is not going to be a nice, neat number like 2 or something. It's going to be kind of a unusual one here. So what I'm going to do here is I'm going to first start here. It says given y equals the arcsine of x, where y is between 0 and pi over 2, let's find the cosine of y. Well, let's start here. I have y equals the arcsine of x. Okay, I'm going to take the sine of both sides. And that is going to give me that the sine of y is equal to x. Well, that makes sense because they're inverse functions. But what does this also tell me? This tells me here, since I'm trying to find the cosine of y and I have the sine of y, what if I draw a right triangle here? Now remember, this is a first quadrant angle, so I can put the first quadrant angle right in there in a right triangle. And what do we know about this? Well, we know the sine of this angle is x, which is the same as x over 1. Opposite over hypotenuse. And if I use the Pythagorean theorem, I get the other leg here to be the square root of 1 minus x squared, which is convenient because I need the cosine of y. The cosine of y would be this, the adjacent, over the hypotenuse, which is 1. Of course, that's just the adjacent. So that tells me that the cosine of y is equal to the square root of 1 minus x squared. Kind of cool. Okay? Get used to that. It's going to come in handy later on. Now it's time to get to the calculus. All right, in the calculus here, we need some derivatives. Now I wanted to point out, and I've got them lined up this way, how similar these derivatives for these 6 trig functions are. It says, let u be a differentiable function of x, so chain rule. The derivative with respect to x of the arc sine of u is equal to u prime all over the square root of 1 minus u squared. Well, the derivative of arc cosine of u is equal to negative u prime all over the square root of 1 minus u squared. See, these are almost the same thing here, just a different sign. Same thing happens with tangent and with cotangent. The derivative of arc tangent of u is u prime over 1 plus u squared. The derivative of arc cotangent of u is equal to negative u prime all over, or the opposite of u prime all over 1 plus u squared. And for the weird one here with the absolute value, for the arc secant, the derivative of arc secant of u is u prime all over the absolute value of u times the square root of u squared minus 1. And then over here, for arc cosecant of u, the derivative is negative u prime all over the absolute value of u times the square root of u squared minus 1. So these are paired up nicely, these pair up nicely, and these pair up nicely. You're going to see when we get to the next section, when we start taking antiderivatives and going from here back to here, that we don't need all 6 of them because these two are so close we could always pop a negative out in front and finagle the constant that way. So we're only going to really look at integrals involving the 1, 3, and 5 there. All right, let's find some derivatives though first. All right, what is the derivative with respect to x of the arc cosine of 3x? Well, according to this formula right here, it is negative u prime. Well, if this is my u here, 3x, negative u prime would be negative 3 all over the square root of 1 minus u squared, excuse me, which is 1 minus u squared would be 3x times 3x, which would be 9x squared. And I am done. That is not going to simplify. We're going to leave the radical in the denominator like that. Look at the next guy here. Let's take the derivative of the arc tangent. I might have one more sneeze left here. Sorry about that. Of 5x squared. I do. Excuse me. So the derivative with respect to x of the arc tangent of 5x squared is equal to, look back here, u prime, which is 10x, because this is my u, all over 1 plus, this is the arc tangent, the one without the radical, with u squared, which would be 25x to the 4th. Be careful there. Now again, it doesn't simplify. You can't cancel here or here because this is a term. Oh, it gets a little bit more interesting on this one. This is equal to the derivative. It would be u prime. This is my u, so this is going to be 1/3 u to the negative 2/3 all over the square root of 1 minus u squared, so that's going to be x to the 2/3. Now you say, well, how does that help me here? Well, this actually will simplify a little bit. I just don't know if I have left enough room. I can certainly put the 3 in the denominator, and I'm going to bring the u to the negative 2/3 down as well. So I have 1 over 3 u to the 2/3 times the square root of 1 minus x to the 2/3 here. Now that's not a terrible answer, but if I wanted to, I could maybe finagle this a little bit, try to get it into the radical. I don't know if it's really worth it. I mean, you could think of this as 3 u to the 4th power, and then be able to, since now I have, well, hang on a second. No, this is square root. I can't do much with that. Nope. Scratch that. Stop here. Okay. Thought I could get fancy, but I can't. Got to start paying attention. All right, this next one here is actually one of the easiest one because we know that the derivative of e to the x is e to the x, so this is going to be u prime e to the x all over the absolute value of u, which is the absolute value of e to the x, times the square root of u squared, which would be e to the 2x minus 1. Now, since e to the x, since e is a positive number raised to a power is always positive, I don't need these absolute value bars. And since I don't need these absolute value bars, these cancel. So I get 1 over the square root of e to the 2x. I'm hoping you can see this okay. My handwriting gets worse as I get closer to the bottom of the page there. 1 over the square root of e to the 2x minus 1. All right. Now, let me put this off to the side here. Let me mention, well, maybe I'll point to it a couple times. Let me mention how important it is to know these guys, to know which ones are opposites and such, and certainly these three, because if you know these three, you've got those three. You know, you're getting an ever-growing list of antiderivatives. Wait a minute, here. No, actually, you know, almost messed up. I have one more problem here, and then here's where your derivatives are. There's a list of them here on 385. I think I just said antiderivatives because I remembered I had one more page here of notes. I'm going to do one more example here because this one simplifies nicely. But you have a list in the textbook, page 385. These are all the derivative formulas that you should know, and they're also on like the flashcards if you have the flashcards to work with and such, whether you make up your own set or you use the set that I'm going to lend you out. But you're going to need to know these rules if you don't already have them memorized by now, because I mean we're practically in chapter 6. We're going to be reviewing for the AP exam before you know it, so make sure that you put these to memory. But let's go ahead and do this one last example here, and I don't remember how long it takes, so I'm afraid to skip a line. But let's try find y prime. Well, the derivative of arc sine of x is 1 all over the square root of 1 minus x squared. And this guy here, this is a product rule. So it's the first one times the derivative of the second one. So I got to think of this as to the 1/2. So 1/2 times the quantity 1 minus x squared to the negative 1/2 times negative 2x, little chain rule there, plus the second one times the derivative of the first one. What a mess this is looking like. Well, I'm going to rewrite this as 1 over the square root of 1 minus x squared plus, now I can cancel this 2 with this half. I have an x times an x, and I have a negative there. So maybe I'll just go ahead and put the minus there for the negative. So it looks cool. And that's going to give me an x squared on top over the square root of 1 minus x squared. And this guy here, he looks pretty normal, but I'm going to go ahead and get a common denominator, multiply top and bottom by 1 minus x squared, and I'm going to get the square root of 1 minus x squared. I'm going to get 1 minus x squared all over the square root of 1 minus x squared. So up top, I actually have 2 minus x squared, 2x squared, all over the square root of 1 minus x squared. And if I factor out a 2, I have 1 minus x squared on top. That's to the first power, and that's all over the square root of 1 minus x squared, which would be like to the 1/2 power. So I could simplify this even further. This becomes 2 times the square root of 1 minus x squared. Kind of cool. This is to the first power. This is the half power here. So you would just subtract the exponents with the same base for dividing, and I get this answer. I would have never thought I would have gotten a simplified answer like that. So you have to be careful not to stop. You're going to have trouble matching the answer in the back of the book, or definitely matching a multiple choice answer like on the AP. And as I mentioned again, page 385 for your differentiation rules. Be sure to look through those. Don't forget to practice, practice, practice.